Okay, so there's one viewer that happens to be me. Maybe some people will pop in a little bit, but I'm going to start and just kind of review some stuff that will be good for you to know for the test. So here we go. The first thing is kinematics. We learned that at the very beginning of the year. But remember, you can only use your kinematics equations if you have uniform acceleration. So if you do have uniform acceleration, then you know that the change in position is going to be VIT plus 1/2 AT squared. You know that VF squared minus VI squared is 2AS. S is the displacement, or the change in the position. That's a delta. It's awful. A little better. You know that VF is equal to VI plus AT, and you also know that the change in position is 1/2 of VF plus VI times T. VF plus VI over half, that's the average velocity times the time. So the displacement, or let's just say the average velocity, is always going to be equal to the displacement or the change in position over time. I don't know why I drew that T backwards. Time. So remember the difference between displacement and distance, right? Displacement is just the final position minus the initial position. That's all that matters. So it doesn't matter if you go to the moon and back. If you ended up where you started, your displacement is 0. So keep that in mind. So it would be a really good idea to have these equations memorized. You probably know them already. But if not, definitely try to memorize these. And remember that you can treat x and y as independent. So, and that goes for anything. It doesn't have to be x and y. It could be a direction down the ramp and a direction perpendicular to the ramp. As long as the two directions are perpendicular, you can break up any vector into its components in those two directions and then treat them each separately. Right, so when you have a ball rolling off of a table, so its initial velocity Vx, that's not going to change because there's no acceleration in the x direction. So this equation, right, the a is 0, so Vf is Vi. You won't ever change the velocity in the x direction. Now in the y direction, the initial velocity is 0, and there is an acceleration. There's 9.8 or 10 meters per second squared. So if you know how long the thing is, because of that, you can find the final speed when it hits the ground. You can find out how long it was in the air, and all sorts of stuff like that. So to find how long it was in the air, we use this equation up here. The VI is 0, so we just end up with h, the height of the table, is 1/2 g t squared, and t is going to be the square root of 2h over g. So that's how long it was in the air, and then if you want to know how far it went, right, and that's it. So that's a 0 launch angle projectile. You want to make sure you're comfortable with those and with projectiles launched at an angle. If this was launched at an angle, you would have to find the initial velocity in the y direction. Sometimes you have to solve a quadratic equation because you'll have a VIT and a 1/2 AT squared. But you guys know how to do that, so don't let it intimidate you. Okay, something that they like to ask is like a ball is thrown from the top of a building at speed v, so from height h at speed v, and it's thrown horizontally. And then they say, well, if you change the speed to 2v, what is the new range? Or what's the new distance? So you have to say you throw it from this height of the speed horizontally, and it goes distance d1 or d or whatever. So if the speed is changed to 2v, what is the new range? Well, and obviously from the equation we had before, we know that the change in position is vx times t. So if you change that to 2, you would just get the new position, d2, let's call it, would be 2d1. So that's easy, but it gets more complicated when they say, all right, well, let's leave the speed the same, and instead let's change the height. Let's make the height 2h. Right? So when we changed the speed, we didn't change the time that it was in the air, but now the speed is staying the same, but the time in the air is going to change. So, like I said a second ago, the change in position we know is 1/2 at squared. So t is equal to the square root of 2h over g. So the time, this would be t1. t2 is going to be the square root of 2 times 2h over g. So there's a couple of ways to do this, and you know that, again, s is just going to be vx times t, so d1 is going to be v times t1, and d2 is going to be v times t2. So what I normally do is I just look at this and I say, well, what do I have to do to this here, right, to make it look like t1? Well, I've got an extra 2 in there, so this is the square root of 2 times t1, and then I would just put that in here, make t2 equal to the square root of 2 times t1, and then I see that d2 is just d1, right? V times t1, v times t1 with an extra square root of 2. So d2 is equal to the square root of 2 times d1. So that's one way to do it. The other way is to just divide. So d1 over d2 is equal to the square root of 2h over g times v divided by the square root of 2 times 2h over g times v. So the v's go away. The 2h over g goes away, and what you're left with is 1 over the square root of 2. So when you multiply, you can say that d1 is equal to d2 over the square root of 2, and d2 is equal to the square root of 2 d1. So that's the most surefire way to do it, is just divide. But if you're comfortable doing it the way that I normally do it, then that's a little faster. But it's up to you. To be safe, you can just do the division, see what cancels out, see what's left over, and you'll get your answer. And you won't accidentally do the wrong ratio that way, which is one pitfall to the way that I normally do it, is that sometimes you get the wrong ratio. Okay, so it looks like one person is watching, so that's cool. One thing to note, there's about a minute delay between what I'm doing and what you're seeing. So if you ask a question, you might not see me acknowledge it for a minute, but there is a little box that pops up on the video. Normally it would be what you would click to go see another video or whatever. But it's right on the screen where my desktop is, and You click that, it opens the question and answer thing, and you can ask questions if you have any. All right, so till that happens, let's see here. So that was kinematics stuff. Definitely know your projectiles, right? And one equation, if you can remember it, that's great. If not, no big deal. But the launch velocity squared times the sine of 2 theta over g, that's the range, right? And remember, for just something thrown straight up in the air, or if you find the y part, you've got the height of the peak is vi squared over 2g, and you've got the time to the peak is vi over g. And, of course, the total time in the air, or the hang time, is 2 times the time to the peak. Right, so if you can remember those, that's awesome. If you can't remember them, that's okay, because you know your kinematics equations. Right, so at the peak, the velocity is 0. So you get minus vi squared is equal to negative, because a is negative g, 2g height of the peak, and height of the peak is vi squared over 2g. Right, so you can just quickly get to that answer anyways, but if you memorize it, that can help too. So it is up to you. Okay. So forces, remember free body diagrams only have a single line for each force, and they have to be labeled. So, for instance, here's a block on a ramp, right? So you know that to solve a problem with a block on a ramp, you're probably going to break gravity up into 2 pieces, right? But one perpendicular, one parallel. But you don't want to do that for the free body diagram. All they want to see is one arrow for each force. So gravity goes down, right? Normal force goes up. And if there's friction, you can put friction, and then if there's a rope or whatever, you can do that too. Now, it's up to you how you want to label it. I mean, you could do Fn like this. You could do mg like that. This could be F friction. I mean, whatever. It doesn't matter as long as it's a unique label and as long as it makes sense, right? Don't call it a rutabaga, but just whatever you want that works for you that's unique. So don't label 2 things T if they're not the same, right? So if I have an object hanging like this, right, the tension of those 2 wires aren't going to be the same. So you can't just call it T and T. Right? It needs to be T1 and T2, TA and TB, whatever you want to do, but they have to be unique labels. So make sure you do that. And then don't try to draw angles, like don't start doing this, right, and putting angles on here or anything else. They don't want to see any of that. All they want is one arrow for each force with a label. Technically, each arrow should be proportional to the size of the force that it represents, but it's rare that they actually score for that on the AP exam. And if they do, they will be clear about it. So they'll tell you to make sure that your arrows are proportional. You still do it because it's proper, but don't freak out about it because they probably won't be looking at it. Just draw the arrows. They don't have to be, measured to the millimeter of proportionality, and then move on. All right, so you get your free body diagram. Once you have the free body diagram, so let's see. We'll go back to the block on the ramp. So let's say there is friction, right? And the ramp has an angle theta. So if I want to know, well, what's the assume the block's moving, what's the acceleration of the block going down this ramp? So I would do the sum of the forces in each direction. On a ramp, I don't want to use x and y. I want to use a direction down the ramp or parallel to the ramp and a direction perpendicular to the ramp. So we call that x prime and y prime. So the sum of the forces, if you did your free body diagram correctly, then it's easy to see what forces go in this equation. And if you'd like to, you can draw another picture. So this is for them, right? This is what they're going to grade. But if you want to draw a separate picture that helps you, you can do that. So I've got normal force, I've got friction, I know that I've got my axes like this, right? And I know that I've got part of gravity going this way, and I know that's mg sine theta, and part of gravity that goes this way, and that's mg cosine theta. So if you want to do a new picture for yourself, that's up to you. You can do that. You could just draw it on the one they gave you if you want to just draw quickly. Here, it's there. Whatever works. But just make sure that every arrow that you drew on here should represent a force you can identify. There shouldn't be... So it's going to slide down the ramp. Right? I told you it's moving. It's going to slide down the ramp. Everybody, not everybody, but a lot of people want to draw an arrow and call this like FA. Or they'll call it MA or something like that. There's no force there. Right? There's... The sum of all these forces results in a net force in that direction. But there's no force you can identify and draw there. That arrow would represent the sum of all the other arrows that I drew on the diagram. And you don't draw that on the diagram, you only draw the actual forces that are acting on the block. So if you can't identify it, don't draw it, but once you've drawn it, you have to put it in your equation. So make sure that every force that has any part that goes in the x prime direction goes in this equation. So those are going to be, I'm going to say down's positive. It's convenient usually to choose the direction that the thing is accelerating as the positive direction. And I know it's accelerating down the ramp, or it's either that or going at a constant speed if friction's equal. But I know it's going, if it's going to accelerate, it's going to accelerate down, so I'll choose down as positive. So that means mg sine theta is positive, and that means the frictional force, which is moving as kinetic friction, is negative. And then I've got the sum of the forces in the y prime direction. So in the y prime direction, I'm saying up is positive, so that's the normal force minus mg cosine theta, which is going down to the left. Okay. I know that this force of friction is going to be mu k times the normal force, which is going to be mu k times mg cosine theta, because my next step is to take this, set it equal to ma, but the acceleration in the y prime direction is 0 because it's not crashing through the ramp or flying off of it. So this is 0. N is equal to mg cosine theta. And I did that because I knew up here I needed the normal force. Where do I have a normal force? Well, there it is. Let's solve for it. Right? And then I just plug this in, and this is equal to ma x prime. So we solve for the acceleration in the x prime direction, which is the only acceleration. So I'm just going to call it a. And the m's are going to cancel out, and I get g sine theta minus mu k g cosine theta. So you can factor out the g if you wanted to, but that's the acceleration. So always start out with writing the equations, right? And then set them equal to ma, and then solve for whatever it is you're looking for. So if you do that, then up here you'll see, okay, well that's what I want, but I've got something that I don't know, right? I want this, but I don't know this. So I look down here and say, oh, well, I've got that, and I know everything else. So there, I'll solve for that. I'll solve for n. Done. I'll plug in it up here, and then I'm finished. So most of the problems you're going to get where you have to do this stuff are probably pretty simple. But if you get lost at all, just make sure that you do both equations for both directions, and then you go from there. Okay. All right, so continuing with forces, you know that we have circular motion, which requires a centripetal acceleration. Whoa, that's not what I wanted. Circle. Great. Okay. So call this the center. It's going to have a radius r. Let's say there's a race car driving around the track. Its velocity at any point is going to be in the direction tangent to the circle. So as it goes around the track, its velocity is changing. And it's always turning towards the center of the circle. Always. So there must be an acceleration that's going towards the center, and we call that the centripetal acceleration. If the car is maintaining the same speed, then we call that uniform circular motion. And if the car is maintaining the same speed, we have uniform circular motion, which means there's no other acceleration other than the centripetal acceleration. If there was, then the thing would be speeding up or slowing down, but it's not. So all the acceleration is towards the center, so it's only changing the direction. It is not changing the speed. We know that centripetal acceleration has to be equal to v squared over r, or omega squared r, however the easiest way for you to work out the problem. So I know that for this race car, right, if it's not gaining speed, if it's only changing direction, then the mass of the race car times the acceleration of the race car, which we know has to be towards the center, is going to be equal to the sum of all the forces that are on it. Right? So you figure out all the forces on the race car, and then you solve for whatever it is you don't know. So you might have a situation like this. Here's your race car. Say it's coming straight out of the page at you. Velocity, right? So it's coming out of the page. So the forces we would have, we'd have mg going down. We'd have a normal force going up. And then a lot of people will want to lose points on their exam by writing an arrow to the right and calling it a centripetal force, and then you'll lose points, and that would be bad, so don't do that. Right? What we do have to the right is a frictional force, and it's static friction between the tires and the road. If the road is banked, then part of the normal force would also go towards the center. So if you think about this car that's driving on the track, it wants to go straight, right? So it would really like to just go like this in a straight line, but it doesn't. It turns. So the friction always opposes the motion you're trying to have. So the motion the car is trying to have, if I draw the track out a little bit bigger, right, the car, which is here, is trying to follow a path that will make it move. Here, let's draw the track a little bit more. It will make it move in a straight line like this, so it would move towards the outside of the track. Right? So there's friction towards the center because the motion would be towards the outside. So to make it not do that, you must have some force pushing towards the center. and that's friction. So it's basically trying to slide sideways, but we're not letting it, or the road and the tires aren't letting it anyhow. So in that case, these forces, they're in the radial direction. So all the things that are radial, either towards the center or away from the center, will contribute to this, right? In this case, mg and normal, well, they aren't in the radial direction at all. Only the static friction is. But like I said, if it was on a bank, then part of your normal force and part of your friction are both in this radial direction. So here's y, here's radial. So you need to take, you'd have to take the part of the normal and the part of friction. Sometimes, like when we have a mass on a string, you end up with gravity pulling down and tension pulling up when it's at the bottom of its swing. And so in that case, you've got one radial force towards the center, another one away from it. But what you need to do is take all the forces that are towards the center and away from the center and put them over here, with towards the center as positive. All right, it doesn't matter if it's on the top of the circle, the bottom of the circle, whichever direction is towards the center, that's your positive direction. And don't be afraid to use the question thing to ask questions if you have any. All right, so that's the main point with circular motion is you've got to do the mass times the centripetal acceleration is equal to all the forces that are radial. There is no centripetal force, right? I didn't write centripetal force anywhere on here. I wish I'd never told you guys there's something called centripetal force because it's really the mass times the centripetal acceleration. That's what we're looking for. And the mass times acceleration is equal to the sum of the forces in the direction of that acceleration. All right, so let's talk about a hump in the road, just like the question you guys had on your free response part of your test, which a lot of you did really well on up until the circular part. So imagine that's a good circle, which it's not, but pretend with me. So we had a radius. We had a car that at the bottom of the circle had some speed. I think it was 17 meters per second, but I'm not going to worry about that. V naught. And the question was, how fast could it go over the hump without losing contact? So in this situation, this isn't going to be uniform circular motion, right? The speed of this car will change unless you're hitting the gas exactly right to maintain the same speed over the hump, which probably won't happen. And in the problem, it told you that he's coasting, right? He's going to coast over. So he's not hitting the gas. So he will slow down on the way up and speed up on the way down. So that's not uniform circular motion, but at the very top of the circle, there is no acceleration that's tangent because, here, let me actually get a circle again. Circle, there we go. Okay, so when he is partway up the circle, right, gravity is going straight down. So part of gravity is just like an inclined plane. Part of gravity is going down like this. Part of gravity is going in like this, and then you've got the normal force going up. So you have some tangential acceleration. When you're over here, you've got the same situation. Gravity's going down, gravity goes in, normal force goes up. So there's tangential acceleration. So that's not uniform circular motion. But right here at the top, gravity goes straight down, right? It does not go in the direction of the road at all. And the normal force goes straight up. So you have no force tangent to the circle. So there is no tangential acceleration right here at the top. So the only acceleration is centripetal acceleration. And that's equal to the sum of the forces that are radial. The direction of the centripetal acceleration has to be down, because that's towards the center of the circle. So going down, you've got gravity. Going up, you have the normal force. So that has to be equal to MAC. Now, when the question is when you're going to lose contact, or to maintain contact, you need this. The cutoff is when the normal force is equal to 0. If the normal force is less than 0, then you're not in contact with the road. If the normal force is greater than 0, then you are in contact with the road. So when the normal force is equal, when the normal force is equal to 0 is our, that kind of defines the state. So whatever they're asking you, whether it's lose contact or maintain contact, you can use 0 as your cutoff. So hang on, I gotta plug in my charger here. And with any kind of problem, when they're asking you what's required for this, or what's required to have this happen, you should be thinking about the limiting condition. So what changes when that does happen versus when it doesn't happen? And once you figure that out, then you'll know what to solve for. So in this case, if the normal force is equal to 0, then I know that I've lost contact with the road. So I'm going to make this equal to 0. And we end up with mv squared over r is equal to mg. And then you just solve for the v. Whatever velocity you find is the fastest speed you can have where you won't lose contact with the road. If you went any faster than that, then you would find a negative normal force, and that would mean you have gone airborne. Right? If you go slower than that, then you'll have a positive normal force, which means the road is pushing up on you. Oh, yeah, you're welcome, Jack. Okay, and then finally, the last part of that, where even if you couldn't do the circular stuff, you really, really should have been able to do this part, but a lot of people just didn't realize what they were supposed to do. They asked you to find the speed that it would have to start at down here in order to reach that speed up here, or the other way around. You know, the speed, what speed will it be at the top? I don't remember which one it was. But it was a question about a change in speed from here, from down here to up here. Right? And they had told you the change in height here. So with that, immediately, if you got a change in height and you've got a curved path, you should be thinking about energy. Even if it was a ramp, you could be thinking about energy if they want a height, right? If they wanted a distance up the ramp, then maybe kinematics would be faster. But if they give you a height and they want to know a change in speed, just go straight for energy, whether it's a straight ramp or a curved ramp, because you know that 1/2. Well, let me take a step back. To make sure you get all the points and to try to keep you from making a mistake, you should start out saying that MEI is equal to MEF. So your initial and your final mechanical energies are equal. In this case, I know obviously there's no spring energy, there's no magnetic or electric energy. So I've got potential energy due to gravity plus kinetic energy. Now, if there were springs involved with this, or if there were some charged particles or whatever, you'd want to list out, even if you didn't think it mattered, if you thought it was 0 at that point, just go ahead and list all the different potential energies plus the kinetic energy. And if you do that, then you're far less likely to forget something, leave it out, and get the problem wrong. And if you do that and you do end up still leaving something out and getting the problem wrong, a lot of times they give you a point for saying you're going to use conservation of energy. And then they give you another point for writing an expression for the conservation of energy. So as long as you write it all out, you're going to get that point. And then in the next step you take, if you say something 0 when it isn't supposed to be, you'll lose points, but at least you got those first two, right? And a lot of times a question like that would only be worth 3 anyways. So they give a lot of points just for you showing that you know what you're supposed to do. And then they give a point or 2 for you actually being able to do it in the end. So they're very generous in that way. Okay, so I know that since I'm going to call this 0 height right here, which, I mean, I guess you could call 0 down here, which would be weird, but you could do that. But I'm going to say this is 0 and this is h, right? Which I think was 8 meters, but I don't remember. So I know this is going to be 0. I know that we'll have some potential energy over here. I know that there'll be some kinetic energy there. And obviously there's kinetic energy here because it's moving. So the let's just say they were asking for the speed that you had to have at the bottom of the hill to have this speed. We'll call VC for the contact speed or whatever, to have that at the top. So I've got 1/2 m v naught squared is equal to 1/2 m vc squared plus mgh. So the m's obviously cancel out. And then we're looking for this v naught, so that makes it easy. V naught is going to be equal to the square root of vc squared plus 2gh. And that should look familiar because it's a lot like one of our kinematics equations, right? Vf squared minus vi squared equals 2ad. That equation comes almost, I mean, you can solve a bunch of algebra for it, but it comes very easily out of conservation of energy. So that's our final speed, and we found it in about 30 seconds. I mean, I talked about it a lot, but if you did this, you would find it in no time at all. So remember, think, unless it's a collision, in which case you should be thinking about momentum. Think about energy first. A lot of times that's the easiest way to solve a problem that involves motion. But if there is a collision, remember, you always conserve momentum. So let's talk about that briefly. It's been so long since I've used this program, since my board's been screwed up. I forgot I have lines and everything. All right, so let's just say there's 2 carts, and they're on wheels, right? And they're going to collide. So this one is going to be 2 kilograms. This one is 3 kilograms. We'll say this is going at 5 meters per second. So I gave it a really strong push, right? And it's going to hit this cart. And I'm going to say they don't stick together. And so let's see. I copy. Cool. All right, so I'm going to say that they do not stick together, that this one goes off in this direction with a speed of, I don't know, let's call it 2 meters per second. So the question would be, so this is the initial, right? This is the final, and then the question is, well, what is the velocity? So the speed, and this is at rest, right? This one right here at rest. So the question is, well, what is v prime here? Right? What's the direction and the speed? And then we could also ask, well, is it elastic or inelastic? So the mistake people will make is they'll say, well, um, it didn't stick together, so it's an elastic collision, so I'm going to conserve energy, and you can't do that, right? You know for sure that momentum was conserved here. That's guaranteed. What you don't know is if energy was conserved. Maybe it was, maybe it wasn't. If you have just two cars hitting each other, it's probably not going to be conserved because the cars are going to crumple, right? And that's going to take some energy. If you have two lab carts hitting each other, it might actually be pretty close. Two cue balls, those don't deform much, so you're going to be pretty close to elastic there. Two balls of clay that you throw at each other, that's probably going to be inelastic because they deform. So there's all sorts of considerations, but the thing is, momentum is conserved, so start with that. So I know that, let's call this, I don't want to write the numbers all the time, so I'll call that M1, M2, and this can be V2 prime. So M1, well, all right, let me take a step back again. So typically for something like this, you're going to get a point for saying you're going to use conservation of momentum, or for writing any kind of expression that indicates that. So if you say Pi equals Pf, there's a point. Then you'll get a point for setting everything up. So the initial is M1 V1 plus M2 V2. Even though I know V2 is 0, I'm going to write that anyways, just to make sure I'm not forgetting anything. And then this is M1 V1 prime plus M2 V2 prime. All right, so I know, and then that would be another point, right? And then you'd probably get a point for solving and finding the velocity. So I know this is 0, right? I know this. I know this. I don't know this right here, okay? So I'm going to solve for that, keeping in mind that direction matters, right? So V1, that was in the positive direction. I'm going to say right is positive. V2, also in the positive direction. So the signs are right, everything's good. If M2 had been moving to the left before the collision, this would have had to be a negative sign here once I put that speed in, because that's moving in the negative direction. You've got to keep track of the directions. All right, so what I end up with is M1 V1 prime is equal to M1 V1 minus M2 V2 prime. So I end up with V1 prime, M1 V1, that is 10 kilogram meters per second, minus M2 V2 prime, that is 6 kilogram meters per second, divided by 2 kilograms, that's your M1. I don't want to write it out again, but it would be good if you solved this all the way and then plugged in the numbers, but I just didn't want to do it right now. So you can see the kilograms cancel out, and you're left with meters per second. You've got 10 minus 6, that gives you 4 over 2, gives you 2 meters per second. And it's going to be to the right, and that should make sense, because you started with 10 to the right. What you have over here is 6 to the right, so you're missing 4 to the right. If this had been more, like let's say this was going at 4 meters per second, then you'd have 10 over here, 10 to the right, you'd have 12 to the right over here. So, sorry, I don't think you guys can see my pen on the screen. I'm not sure if you can or not. So you would have 10 over here, right? You'd have 12 over here. So you know that you've got too much in the x direction after the collision. So that would tell you that the other cart would have to be going to the left. Okay, so the other part of the question was, is it an elastic or an inelastic collision? So usually that's like a 2-point question. So you say that you're going to set the energies, or you're going to just calculate the energies, and if they're equal, then it's elastic. So you find KEI, and that was just 1/2 M1 V1 squared, and KEF is 1/2 m1 v1 prime squared plus 1/2 m2 v2 prime squared. And then if they're equal, it was elastic. If not, it was inelastic. So what we've got is, to start with, we had 1/2 of 2, that's 1, 5, that's 25, right? And then to end, we had, let's see, 0.5, or pardon me, 1.5 times 4. So that is 6. And we had 4, so we had 10, right? So 1/2 of 2 times 4 is 4, 6, 10, yeah. So I started with 25 joules. I ended up with 4 plus 6 with 10 joules, right? So that means it was inelastic. Sometimes they'll tell you that it was an elastic collision, and if they tell you it was elastic, elastic, not inelastic, but elastic, then you know that energy was conserved as well as momentum, and you can use that when you're solving your problem. But other than that, you should not be looking at energy at first. You should be doing momentum. Are the questions in multiple choice section going to Yeah, Cadence, you can't really say one way or the other. The distribution is going to be, and you can get this off of the College Board site. Hopefully you've already been looking at it. Let's see. Come on, computer, you can do it. All right, maybe you can't do it. I'm trying to open this file. There it is. Oh, man. Okay, so let me show you this. Oh, screen share. Yes, this. Great. Okay, so... Okay, here is the breakdown. But come on, don't be like that. All right. So here's the breakdown of the topics. You've got Newtonian mechanics, 35%, and then they give you, the percentages. Now, a lot of these things are going to show up in other parts, right? So you're going to have a question about momentum. Well, that's going to have some kinematics component to it, or something like that. Circular motion rotation, 4% is kind of like they're fooling you there, because it's a lot more than 4%, because there might only be 1 or 2 questions about just strictly there's this speed, there's this radius, what's the centripetal acceleration, but there'll be several questions that will rely on you understanding about circular motion to do force questions. So yeah, but just looking at the percentages, you can get an idea of how much everything's weighted. Fluids and thermo is a total of 15, electricity and magnetism a total of 25, with magnetic fields and electromagnetism being 9% combined. Waves and optics, whoops, go back. Waves and optics 15, atomic and nuclear 10. But the thing is, you can't really say, what percentage it's going to be on the multiple choice, because you just don't know how they're going to distribute it between the free response and the multiple choice. So they will cover roughly those percentages, but the question is, how much of it's going to be on the free response and how much is going to be in the multiple choice. In the practice test I gave you guys, they had a ton of electricity and magnetism stuff on the test, on the multiple choice test, pardon me, because they didn't have any on the free response. So that was kind of how that worked. Okay, can I change what screen I'm sharing with you guys without turning it off and back on? Yeah, this is a really neat thing they've got here, and it's a lot easier than doing what I was doing with having to use XSplit to choose which part I wanted you guys to see. Because now you just see my Active Inspire screen no matter what else I do, which is awesome. But it's bothersome, some of the stuff they do. It makes it weird and hard to figure out. I think they'd want to make it user-friendly. But anyways, it's definitely, I mean, I'm not complaining too much. It's a good tool to have. So yeah, that's the deal with the distribution. You just can't tell. But overall, those percentages will be pretty accurate. It just depends on what part of the test they want to focus on different things in. So yeah. All right, momentum, very good. So let's talk about simple harmonic motion really quickly. Whenever they ask you a question about simple harmonic motion, if it's a general question, you need to make it specific. So they say, okay, when something's in simple harmonic motion, this is true. Then don't just try to think about simple harmonic motion, think about something in particular. You could think about a pendulum, but I would choose a mass on a spring. Because with a pendulum, there's angles and different things going on and curves. With a mass on a spring, there's the equilibrium position and there's the amplitude, and you know the force is always going to be the spring force, which is kx, always pushing towards the center. So the acceleration, that's ma, is equal to kx, right? Technically it's negative kx, but that's right. So you know the acceleration is going to be proportional to the displacement. That's obvious. So I would always set that up for yourself. So they ask you, at equilibrium, these two things are at a maximum. Well, the answer is speed and kinetic energy. But you know, you might not know that off the top of your head. But if you look at the spring and you say, okay, well, at equilibrium, I know that the spring is unstretched. And if the spring is unstretched, then the potential energy in the spring, 1/2 kx squared, well, that's 0. So if the potential energy is 0, the kinetic energy is at a maximum. And I also know the acceleration is going to be 0. And if the acceleration is 0 and it's about to change, the acceleration was in the direction of the velocity, and now it's going to be in the opposite direction. So it must have been at the maximum speed right there, which, of course, if kinetic energy is at a maximum, so is the speed, but whatever. Or if they say at maximum displacement, what are two things are at a maximum? Well, you know the acceleration is at a maximum if x is at a maximum, and you know that the potential energy is 2. So if they ask you a general question, just think about a spring and figure it out. Also remember the period of a pendulum is going to be 2 pi square root of L over G. If you can't remember if it's L over G or G over L, think about the units. This is meters per second squared. So the meters cancel out, the second squared comes up to the top. When you take the square root, you get seconds. And the period is the number of cycles every second. All right, mass on a spring, which you ms, whatever, 2 pi square root of m over k. Same deal. K is newtons per meter. A newton has a meter per second squared in it. Right. So, so that works out as far as the units go. But make sure you memorize these. Right. Know this and this. You'll get some easy points. And if they ask you about a ratio, remember what I said earlier, the easiest way is to just divide. So if they tell you, okay, the period is this, all right, well, that's T1, and we're going to change this. All right, well, that's T2. So T1 divided by T2. So let's say it's a pendulum. So you had L over G, and they say, okay, well, now we're going to double the length of the string. So that's 2 pi square root of 2 L over G. So the 2 pi cancels, the L cancels, the G cancels, everything cancels except for the square root of 2. So you find that T2 is equal to the square root of 2 T1. Right. That's the surefire way to do it. You could have also just looked and you can see that there's an extra square root of 2. for T2, but whatever works best for you. Another thing they might do is say, well, we're going to go to a planet where the radius is different or the mass is different. And how does that change things? So remember, gravity is big G, m1, m2 over r squared. R is the center-to-center distance. So they give you a distance from the Earth's surface. Remember, you need to add the radius of the Earth to your r. Okay, so knowing this, then if we take an object, like say the weight on the end of a pendulum, then if it's on some planet, whatever that planet is, we're going to give that planet a mass big M and a radius big R. Okay. So you know that your G, your acceleration of gravity on that planet, is going to be, actually, you know what, let me, just to be really clear, let's just call this A. And you know that on Earth, that would be G. Right? But let's just call it A for now. So that's going to be big G, big M over big R squared. All right, so that's your acceleration. And you know the period is 2 pi square root of L over G. So if the acceleration, G being the acceleration, changes, then you're going to change the period. So you need to figure out how it changes. All right, so let's say we are on Earth. So G is big G, mass of Earth, right? Radius of Earth squared. And then they tell you, all right, we're going to go to a different planet. So I'll call it G prime, where the mass is doubled and the radius is, I don't know, let's say it's tripled, so 3. Right. So what you end up with is 2/9 of G big ME over RE squared. So what you see is you've got 2/9 of the original G. Now, if that works for you, that's great. If not, again, you can just divide, right? Original G divided by G prime. Now you're going to find that G prime is 2/9 of G. And once you find that, you plug that in here, right? And you're going to find your new period. So that's going to be the square root of 9 over 2 times the old period. So 3 over square root of 2 times the old period. All right. So yeah, that's gravity. Remember another thing about gravity, orbital speed. Right? If you have a planet orbiting a sun, if you have a moon orbiting a planet, anytime you have something relatively small orbiting something big, then you know that it's going to make somewhat of a circular path. They won't ask you about elliptical stuff much. If they did, it would just be an energy thing. So we're going to assume a circular path, and we know that the only force on the little thing is going to be the force of gravity pointed towards the big thing. Oh, that's another thing, too. Remember, you got the moon and the Earth, right? Moon, much smaller than Earth. They'll ask you, well, if the force on the moon from the Earth is F1, then is the force on the Earth from the moon, F2, greater than, less than, equal to, you know, something weird like that. But you know they're the same, right? If the moon pulls on the Earth pulls on the moon just as hard. Right? Okay, but anyways, that force, right, that is towards the center of the circle, and that is the only force acting on the thing. So the centripetal acceleration times the mass has to be equal to the sum of the forces. That's going to be Fg, that's going to be big G, m1, m2 over r squared. So we know the acceleration is v squared over r. That's g m1, m2 over r squared. Whichever m this was, let's call it m2, that's going to cancel out. So the mass of the satellite will not affect the orbital speed. Okay. So also an r goes away. So if you're told the radius and you're told the mass of the thing it's orbiting, you can quickly find the orbital speed. Right? It is going to be the square root of g m over r. And that's it. If you want to find the period, remember period is 2 pi over omega. Omega is v over r. Right, so you can find it that way. You can also say, well, it's going to be the circumference, however, whatever circumference that is, divided by the speed. So if I straighten this out into a straight line and I divide it by the linear speed, then I'm going to get the period as well, because that is how long it takes for one revolution. Oh, shoot, I said that wrong earlier. When we were talking about period, I said that the period is the number of cycles per second, and that is frequency. The period is the number of seconds for one cycle. Sorry. Okay, so you know that is your period. So the period is 2 pi r over the square root of g m over r. So if you square both sides, you get that t squared is equal to 4 pi squared over gm times r. Yeah, cubed, because that gets squared and that's 1, yeah, r cubed. So t squared is proportional to r cubed, and that is Kepler's third law, which you guys are responsible for knowing how to derive. And I just derived it for you. It just takes a second. Okay, kinematics, projectiles, forces. Talked about energy a little bit. Momentum, simple harmonic motion, gravity. Okay, fluids. So remember A1 V1 is equal to A2 V2. That is the continuity equation. That says that whatever volume goes in has to come out. If a pipe is filled with water, and I want to put a gallon of water in one end, a gallon of water would have to come out the other end. There's no other way, since we assume water is incompressible. Also, recognize that if you take the cross-section of a pipe and you multiply it by the velocity, that's meters per second, right? So that's the distance it's traveling to the right every second. So you end up with a volume. So if you do A times V, then it's that much volume every second. So imagine that as part of a larger pipe. So this slug right here, that passes by a single point, so let's call this one point in the pipe. So that much stuff will pass that point every second. And that's what that means. So there's a question that was on the practice test that I used for your final that I left off, where they had a river and they gave you the dimensions of the river and how fast it was flowing, and you had to figure out what volume that was. Right? And all you need to do is cross-sectional area times velocity. And if you want to know, well, how much mass is that? Well, they tell you, they would have told you how many kilograms to the, liter or meter cubed is probably what they would have told you, is 1,000 kilograms per meter cubed. So that's really important. Continuity equation, being able to work out volumes, volume per second, make sure you're comfortable with that. So if you combine this and Bernoulli's equation, you can solve problems where things change height, where hoses change diameter, things like that. So remember, Bernoulli's equation says that the pressure at a certain point plus the density times G times H at a certain point plus 1/2 the density times the velocity squared at a certain point will be equal to some constant. So at any other point, you can set all this equal. So at another point, P2, right, all this is equal. So that allows you to find pressures or velocities or different things. Oftentimes, you're going to find the velocity using the continuity equation. So they'll tell you there's a pipe with this width, and there's this pressure, and it's going at this speed, but that's down here. And then we go up to the top of the house or whatever, and the pipe is now smaller. And they'll tell you the change in height, right? And they'll tell you the change in the radius. Right? So there's a radius there, there's a radius here, R1, R2. Now remember, the radius squared is proportional to the area. So this is pi R1 squared, this is pi R2 squared. The pi's cancel out, right? But you've got to square the radii. So if R2 is only half of R1, then this is pi R1 squared, and this over here times V. And then this over here is going to be V2 times pi R1 squared over 2 squared, so it's over 4. Right? So don't make the mistake of just saying, well, it's half, so it's going twice as fast. It's not. It's actually going 4 times as fast. All right, so be careful with that. So you know the height, you'll know the change in height, you'll know the pressure down here, they'll tell you that. The pressure at the faucet is this, right? And then the question will be, well, what is the pressure up here? So you just plug in and solve, and you're good. Right? Remember, if something is open to the air, the pressure is the atmospheric pressure. So if I have a hose, and let's say it has, you know, some kind of cap on the end, whatever, it's a spray nozzle and you're not squeezing it, but there's a hole in it. So there's a hole right there, very tiny hole. So the question is, well, what is the, what's the height? How high is that going to go? So to figure that out, you'd want to know the speed of the water leaving this, right? So we've got the pressure, which they'll tell you the pressure is whatever it is. The height's not changing, right? The hose and all that's at the same height, basically. Although you could actually use the height to find how high the string is going to go before it falls down, but we'll talk about that later. So the height, we'll say, we'll leave these out for now. Come on, there you go. The V1, well, this water's not really moving in here, right? So then what you're left with is, well, we've got P2 and we've got V2. Well, P2 is atmospheric pressure, so that's 1 atm or 100,000 pascals, right? So then the only thing you don't know is V2. So you can find that, and once you know that, you can figure out how high this thing goes. Because you know the acceleration is going to be g. So you can work out the height. I feel like since you know at the top it's going to be 0, I think you can make this 0 and then keep the rho GHs and then solve for the H that way. But I don't remember, and I'm not going to take the time to work it out right now. But if it comes up, just use this and you'll get there. Once you know V, you know the height of the peak is Bi squared over 2G. Okay, so that's Bernoulli's stuff. Remember, pressure, if you are in a tank that is open like this, you've got atmospheric pressure here, some depth down here, H. Right, you want to know, well, what's the pressure there? well, that's just going to be rho GH. The buoyant force, if I have a cube of something in here, right? Well, the buoyant force is going to be equal to the weight of the water you displaced. So that's going to be rho of, or the liquid, whatever it is, rho water times G times the, well, let me leave the G off for now, times the velocity of the object or the displaced water, because it's not always completely submerged, right? Times G. So this, remember, rho density times volume, that gives you mass. There's questions where you'll have to use that, like if something is floating, partially submerged, and you want to find out the density of it, well, you're going to find that mg is equal to the buoyant force, rho of the water, v displaced, times g. But that doesn't give you the density of the thing that's floating, so what you need to do is change this into density of the thing times volume of the thing, right, times g. And then you can solve, because they'll tell you the percentage that's submerged, right? So that's going to be v displaced over total. They'll tell you that, so you'll know that ratio. And you'll know water, you'll know G, you find the density of the thing. So no big deal. Do we need to memorize Bernoulli's law? Yeah, I would. Yeah, I would try to memorize Bernoulli's equation. And it's not too tough because it's really, energy stuff. So you got to remember that it's pressure, but that's easy because the whole thing's about pressure, right? And then you've got gravitational potential energy, and you've got kinetic energy, each with a rho instead of an m. So it's pretty easy to remember, hopefully. Okay, remember, be really careful when you do free body diagrams for stuff with fluids. People typically forget things. So let's say there's some cork floating like this, and there's a string tied to it. So when you draw the free body diagram for that cork, make sure you draw everything, and don't draw anything that's not there. So I know there's a rope, there's obviously tension going down. I also know there's gravity going down. And I know there's a buoyant force going up. Okay? So make sure you don't forget something. People oftentimes forget gravity in that situation. And they just do the tension and the buoyant force. So be careful of that. Let's see. Remember, pressure is force over area. The fluids we deal with are incompressible. So if you have a hydraulic system, or really anything, but a sealed container, right? I push down here with some force. You divide that by this area, and that gives you the pressure. I transmit that pressure throughout this entire container. This area here is much larger. The force here is going to be equal to the pressure times the area. The same pressure that I applied over here times a much larger area gives me a much bigger force, and that's how hydraulics work. But the trade-off is, for every, say this is 10, the big one's 10 times as big as the small one. For every meter that I push the small one down, the big one only goes up by 10 centimeters. So you still conserve energy. You don't get anything for free. It just makes the work easier to do. Just like a pulley makes work easier to do. That's all it does. Okay. Remember, water finds its own level. So if you have weirdly shaped stuff, the water that you pour into this weird looking container will all find the same exact height. That has to do with pressure being equal and stuff like that. So remember that. Also remember that as long as you are at the same depth with the same liquid, it does not matter what the shape of the thing is. So You can have a container like this. You can have a container like this. You can have a container that goes like this. I mean, anything, doesn't matter. At the bottom of each of these containers, if you have the same amount, or not the same amount, but if you have the same level of water, at the bottom of the container, the pressure will be the same. And so be aware of that. I feel like that's most of the fluid stuff. If you guys have any other fluids questions, definitely let me know. But I think that is the main stuff that I can think of right now. So I'm going to move on to thermodynamics. And for people who have just started watching or started a little while ago, there is a delay of about a minute between me saying something and you hearing it. So if you ask a question and I don't respond for a little while, that's part of the reason. The other reason is I can't see your questions while I'm working on this screen. I guess I'll fix that though. Yeah. Oh, there we go. Yeah, so now I can see your questions, but still there's a bit of a delay. So, okay, so thermo. Three really easy things that you can know about thermodynamics that'll let you get questions right. The heat that it takes to raise the temperature of something. MC delta T. You guys know that, right? Actually, there's four, because I forgot about the thermal expansion and conductivity. So you've got the change in the length of something is the coefficient times the length. There's also times the original length. There's also an area one, right, and a volume one. So, and remember, when things expand, everything expands. So if it is a can, a paint can, like this, even if it's got like a thick wall, right? So when this thing heats up, the outer diameter gets bigger and the inner diameter gets bigger. Everything expands, right? So knowing those expansion things and knowing the conductivity stuff, so Q, the heat that's conducted through a slab. So the slab would be something like this. Oops. So we're going to say that this is the high temperature over here, this is the cold temperature over here. This could be like a window, this could be a metal bar, this could be anything, where you have a higher temperature on one side and the colder temperature on the other. That heat energy is going to move through that material from the hot side to the cold side. So we're going to have some Q going this way. So we want to figure out, well, how much, how fast, right? So there's a conductivity coefficient K. And then the rest of the equation, you should think about as far as whether it's on the denominator or numerator. Just think about what makes sense, right? The longer it is, right, the longer it should take. But the wider it is, right, the more surface area on each of the sides where there's a differential. So the surface area here and here, that would make it go faster, right? So the A, the cross-sectional area should be on top, L should be on bottom. Okay? Then you've got the difference in the temperature, right? A bigger difference in temperature is going to mean more heat's going to flow faster. And you've got the time. So in a certain amount of time, with these conditions here, you're going to get that much heat. Or you can divide it and you can say, well, the power, the rate at which heat is transferred, is Ka over L delta T. So I lump this all in as one thing that's easy to remember. Right? So you got one, you got two. Efficiency is another one, right? So with an engine where they give you efficiency, I'll leave that there for a second. Remember, we're going to take in, or basically there's a certain amount of energy that's available. Right? When water flows through a dam, there's a certain amount of available energy there from the water moving. We don't get all of that. right? When we burn gasoline, we don't get all of that. When you ride your bike, not all of that energy is put into making the wheels move on the road. Right? So there's always some efficiency. The efficiency is the productive work you get out of whatever the thing is, divided by the energy that you take in. So whatever productive work you get out divided by the total energy that you took in, or that you started with, or that was available, that is your efficiency. Okay. Now, what's left over is lost. And in an engine, we say that that is exhausted. So the energy exhausted is going to be whatever you took in minus, well, let's not say it that way. Let's say energy in minus work out. So I took in 100 joules, right? I did 60 joules of productive work. I have a 60% efficient machine, and I'm exhausting 40 joules of energy. So of the 100 I take in, 40 joules goes somewhere else. If it's an engine, we say it's exhausted. In the test question, where we were raising that water, right? So there was the part with the engine, and there was exhausted heat. But then we also said, well, the engine gave us this much energy to use to raise the water. Some of it went to raising the water. Some of it went to noise, turbulence, heat, all those other things. So efficiency, right? That's your third easy thermodynamics thing. Okay. So the fourth one is this equation, right? So this says that the change in internal energy, which is proportional to temperature, the change in internal energy is equal to the heat plus the work. Right? Now, as far as whether the work is going to be positive or negative, you need to think about, well, what should this do to the temperature of the gas? If I push a piston in, I'm doing positive work, and that should make the temperature of the gas go up. So I should add that. If the gas pushes the piston out, the gas is doing positive work, and it should lose energy, it should lose heat. And so you should subtract that. As far as the heat, if the gas absorbs heat, it's positive. If it gives off heat, it is negative. Right? So that's really simple. If they ask you a question, like there was one on your test, where they said what was it, something like a gas does 400 joules of work, and the energy changes from, like, I forget, like 600 joules to 900, or 900 to 600 maybe. I don't remember how it went. So that's work. Let's just make it a new problem. 400 joules of work done by the gas. Right? Internal energy. The change in internal energy was negative 300 joules. We lost 300 joules of internal energy. Well, we should have lost 400, right? Because the gas did 400 joules of work. So delta U is equal to Q plus W. So that is equal to, that's negative 300. It's equal to Q. The gas did work, so that should make Q go down. So that's minus 400 joules. So Q was 100 joules. Right? So those are simple questions if they ask them like that. If they show you a graph, it can get a little more complicated, but if you can read the graph, you'll be fine. And typically they're going to tell you it's an isotherm, or it's adiabatic, or it is constant volume. So that's your fourth easy thermo thing, right? And then we can also remember isotherm means no change in temperature, no change in internal energy, right? Adiabatic, no Q, right? Q is equal to 0. Notice I don't say there's no change in heat. We don't do change in heat and change in work. heat and work go into making the thing change. Right? Things that are state variables, temperature, internal energy, entropy, pressure, volume, those are state variables, and we have a change from one state to another. Between A and B, there's different ways to get from A to B. Different paths will have a different Q, and they'll have a different W. But they'll always have the same change in temperature, the same change in pressure, all that stuff. So if I go from A to B, like this, that looks like an isotherm. That's a nice inverse curve, right? So that's going to have a particular Q and a particular W. The W, remember, is the work under the curve, right? And in this case, since this is P and this is V, the volume is expanding, so the gas is doing work, so we would say this is negative work, right? Because in the equation, plus W, we'd want to subtract that to make the delta U go down. All right, so if that happened, we must have taken in the same amount of heat, right? Because on isotherm, we know that delta U is 0. Right? But if instead I go like this, constant pressure, constant volume, from there to there, there's different Q's and different W's, right? The work that's done between here and here, from A to B, is going to be the area under the graph, which is going to be the area under the straight line here, from left to right. Right? There's work done there. There's no work going down to B from there. Right? So, yeah, there's going to be heat given off as you move down to B. But anyhow, there's going to be a different Q and W if you follow the top path compared to the bottom path. All right, so adiabatic, there's no heat added or lost. There's no Q. Q in this equation is 0 if it's an adiabatic curve. If there is constant volume, remember, work is force dotted with displacement, right? So if you don't move the piston, if you don't change the volume, you can't have any work. No work, right? So isotherm, constant temperature. Adiabatic, no change. What do you mean? Adiabatic, there's no heat added or removed. Constant volume, there's no work done. Right? So remember those, and you'll be all set. Remember, if you follow a complete path, so like in this case, if I went, let's call this C, I guess. So if I went from A to C to B back to A, as I go around that loop, I get back to A. So the change in internal energy along this entire path has to be 0. So if I add up the change from A to C, the change from C to B, and the change from B to A, they all have to equal 0. So remember that, and that will help you solve problems as well. Okay, so that is thermo, and we've been going for a while. Let's see. All right, remember Snell's law. You should have this memorized. N1 sine theta 1 is equal to N2 sine theta 2. Remember that the N, the index of refraction, is C over V. C is the speed of light, V is the speed in a material. You know that N is always greater than 1 unless it's air. For air, N is equal to 1. So you know it has to be C over V, because that way C is bigger, V is smaller, you get a number bigger than 1. For the critical angle, remember the critical angle is the angle where if you're incident at that angle, then it will bend the light all the way down into the material, and none of it will leave. So remember, these angles are measured from the normal, right? And that will turn it this way, and it will not leave the material. So the so this is sine theta critical. This is going to be 90 degrees, so the sine of that is 0. The sine of that is 1. So what we end up with is N2 over N1. Right? So your N2 has to be smaller than N1. So if you're going from air into anything, you can't have a critical angle because going from air into anything else causes the light to bend away from the surface. But if you're going from something into air, then there's always a critical angle because air has the smallest N. So, but either way, your N2 has to be smaller than your N1. The bigger the difference, the smaller the critical angle, right? Because the more bending happens. So that's critical angle. Make sure you're comfortable with that. Make sure you know all your ray tracing stuff. Remember the parallel ray and all that. Parallel, focal ray, middle ray, center ray, all those things. Remember the mirror equation is also the lens equation. All right, but you always have to say that the object is positive to make it work with lenses, right? With mirrors, the object is always positive because it's always in front of the mirror. With lenses, the object is always behind the mirror, which is behind the lens, which is the negative side of the lens. But we always say the object is positive because we're using this equation where you need that to be positive to have the geometry stuff work out. So make sure you know that. Make sure you commit that to memory. You should have it already memorized. Okay, optics. Okay, the atomic stuff, or well, I'm not even going to talk about the interference stuff. We've talked about that so much. The atomic stuff, remember, E equals HF. Memorize that, please. All right. For a photon, the momentum is h over lambda. Memorize that. Okay. These are photons. Photons only. So if you know the frequency something's oscillating at, you can't do HF and find its energy, right? It doesn't work that way. This is photons only. Now, for particles, right, it doesn't really show up much with a baseball, but if you're talking about an electron, the de Broglie wavelength, right? Oh, that looks like decibels. The de Broglie wavelength is going to be h over the momentum. So that's this equation over here rearranged. This is for particles, right? The others are for photons, so make sure you're comfortable with that idea. The energy level stuff, remember when an electron absorbs energy, it will jump up an energy level if it can. Right? It'll only take a photon that gives it exactly enough energy to move to a new energy level. Otherwise, it'll let it pass through. And then the when it drops down, it gives off photons with the appropriate energy. So the drops can happen from any level to any level, right? So if you're starting here, you can jump all the way down. Or you could jump here first and then go here. Right? Same goes if you started up here. I can go all the way down, or I could jump 2 and then 1, right? I could jump 1 and then 2. It's whatever, right? You can go any path you want. So they're going to go through all these paths. You're going to see all these different wavelengths of photons. Each one of these gaps, right, represents a different wavelength you can see. So in this case, there's going to be 1, 2, 3, 4, 5, and then 6. So there's 6 different possible ways that an electron can change energy levels. So there's going to be 6 different wavelengths of electromagnetic radiation that are emitted when electrons are dropping down from that level. The photoelectric effect, we had that on our final. Remember, to find the cutoff frequency, you make the K max equal to 0 because that's when you're just barely freeing an electron. The slope of the graph of K versus F is H. The slope of the graph of Vs, which is K divided by an electron, the slope of that graph is H over the charge of an electron. So that is h over e times f minus v over e. And remember the y-intercept, right? It's actually the stopping voltage is 0 for anything less than the cutoff frequency, says the maximum kinetic energy. But if you trace this down here, you find phi, right? Or you find phi over e, either way. So it's easy to find the work function from the graph. Atomic stuff, or that's atomic stuff. Nuclear stuff, I think you guys are okay. E equals mc squared for the mass defect, converting to energy, and then balancing equations, hopefully. If I tell you that I start off with carbon 14 and I end up with nitrogen 14, you can tell me that there's a beta particle there because that has a charge of -1. Remember, the bottom number is charge, the top number is mass. Okay. All right, and then we had all of the electricity and magnetism stuff. I'm not going to get into a ton of detail on this because we've been talking about it a lot lately. Well, there's circuits too. Make sure you're comfortable with circuits. Power, I squared R, right? IV, V squared over R. Make sure you can deal with kilowatt hours, how much you pay for energy, right? So money per kilowatt hour. But as far as the electricity and magnetism stuff goes, remember the electric force on a charged particle will always, always, always be equal to E times Q. I don't care what kind of field it is. If you know the value for E, then you know Q. So remember that. Remember that voltage, the change in potential for a uniform field, is E times D. That's a uniform field. Okay, and then Q, or pardon me, U or PE, potential energy, is QV. The change in PE is Q delta V. All right, so there's all the point charge stuff, which I hope you guys know, but make sure that at the very least you understand that FE is equal to EQ. For a uniform field, V is equal to ED, so two parallel plates, right? There's some V here. There's some D. Right? You know how to find E, right? E is V over D. And then you got to know that whenever they tell you the change in potential, so I move a charge from here to here. It started at 0 volts, now it's at 10 volts. Well, the change in energy is just Q delta V. You don't have to do anything else. It's just Q delta V. So make sure you know those things. For magnetism, so remember magnetic forces cannot do work on charged particles. All right, they can change the direction, they cannot change the speed. Okay, delta KE is 0. There's no work done. Right. Remember the work energy theorem, right? The net work is equal to the change in kinetic energy. Okay. So the work in this case, I've got V, I've got F. Right? V represents the change in position, right? So work is F dot D. If the angle is 90, then FD cosine theta is 0. So there's 0 work, there's 0 change in kinetic energy. I should have mentioned the work energy theorem earlier. Please remember the work energy theorem. Please. Yeah, that's the biggest thing I can tell you. You got to remember that. They will almost certainly ask some kind of question to see if you know that. Remember, with magnetic forces, they're always towards the center of a circular path that the particle is following. So if there are no other forces going on, then if the particle goes in like this, it's going to make a circle. And if the field is strong enough and the velocity is low enough and the mass is big enough, it can make a full half circle there and come out the other side like this. You have the radius. Okay. So at any point along here, velocity is this way, the force is towards the center. The magnetic force, if it's the only force on there, you can say that MAC is equal to FB, which is QVB. Right? Sine theta, but perpendicular. So that means that mv squared over r is equal to qvb, and you can solve for whatever thing out of there you need to know. Now also remember, if we have two charged plates, and we also have a magnetic field, and we're sending a charged particle through, we can set this up so that it makes the thing go straight. So a positively charged particle going this way with a B field going into the page would have a magnetic force going up. So we would want to have this be the positive plate and that be the negative plate, so the E field goes down, and we end up with FB going up, FE going down, and if your speed is correct, which remember, QE is equal to QVB, so that speed is E over B, then that particle will go through undeflected. It does not matter if it's positive or negative. As long as the E and the B are oriented correctly, a positive or a negative particle will go through undeflected, because for a negative particle, FB would be down and FE would be up. With the E field going down, a negative particle will experience a force going up. Okay, so that's all I got. I really hope you guys do well tomorrow. I know that, I mean, God, you've done like what, almost 30 homework assignments. You've done a lot of work, and we've done a lot of work in class. We've taken a lot of tests and different things, and I know that you know most of the stuff, right? And I really think you guys can do well, and I'm looking forward to it. So, good luck tomorrow. And if you have any more questions, you can definitely email me, and I will try to answer them. And you guys have a great day. And don't stay up all night studying, right? Get some sleep. Eat some breakfast, eat some lunch. All those things. All right. You guys take care. Good luck.